In this video, we are going to talk about a root finding method known as secant method. In this method, 2 points are chosen on a curve and through them a line is drawn. Wherever that line intersects on the x-axis, that is the new approximation to the root. And this is repeated and we get root. So what do I mean? That let me plot a curve and there are two chosen points, x0 and x1, and through these two chosen points a line is drawn. This is known as secant or secant line, and this point is the root, and this point is where the secant line cuts this x-axis. Now we can see that this new point is closer to the root than the earlier points. So earlier points are this x1 and x0, and as we can see that both these points are away from root as compared to x2. These two chosen points could be on the same side of the curve or maybe at the opposite sides. The equation for the secant may be written as x1 minus x2 divided by f at x1 equal to x0 minus x1 by f at x0 minus f at x1, and solving this equation we get x2 is equal to x1 minus f at x1 x0 minus x1 by f at x0 minus f at x1, or we may also write down it as x0 is equal to x1 minus f at x1 x1 minus x0 by f at x1 minus f at x0. Now the same method may be repeated and we can find out the next approximation. The next approximation will be given by x3 equal to x2 minus f at x2 into x2 minus x1 by f at x2 minus f at x1, and if we continue then we can obtain a general formula, and that formula will be xn plus 1 is equal to xn minus f at xn xn minus xn minus 1 divided by f at xn minus f at xn minus 1. Now this we can continue until we obtain the approximation to the root with desired accuracy, or we call it tolerance. So this method can be considered an approximate to Newton-Raphson method. Newton-Raphson method is given by xn plus 1 is equal to xn minus f at xn by derivative of f at xn. So if we use an approximation for this derivative as f at xn minus f at xn minus 1 by xn minus xn minus 1, then we can obtain the secant formula. Now in this method, let us see the rate of convergence so to understand it, let us say alpha is the actual root of a function. Now also let us consider that xn is nth approximation to the root. Hence, I can write down that nth error is equal to xn minus alpha and n plus 1th error is equal to xn plus 1 minus alpha. Now we have xn plus 1 is equal to xn minus f at xn, xn minus 1 divided by f at xn minus f at xn minus 1. What I do, I subtract alpha from both right as well as left hand side. So I can write down n plus 1th error is equal to xn minus f at xn, xn minus 1 by f at xn minus f at xn minus 1 minus alpha, or I can write down xn minus alpha minus f at xn into xn minus 1 divided by f at xn minus f at xn minus 1, and this is nth error. Now let us write down this whole thing like this, and here in this parenthesis I add and subtract alpha. So I can write down it like this, divided by f at xn minus f at xn minus 1, or the nth error can be written like this, can be written like f at xn into nth error minus n minus 1th error divided by f at xn minus f at xn minus 1, and taking this as an LCM we can solve it. So nth error multiplied by f at xn minus nth error into f at xn minus 1 minus nth error at f at xn plus n minus 1th error multiplied by function value at xn divided by f at xn minus f at xn minus 1, and this and this will cancel out. So I can write down it as n minus 1th error into f at xn minus nth error f at xn minus 1 by f at xn minus f at xn minus 1, and let me say this is equation number 3. Now in the next step I multiply and divide the equation with xn minus 1. So I can write down xn minus 1 divided by f at xn minus f at xn minus 1 multiplied by n minus 1th error multiplied by f at xn nth error f at xn minus 1 divided by xn minus 1. Now let me multiply and divide the numerator by this factor. So I can write down xn minus 1 divided by f at xn minus f at xn minus 1 into f at xn by nth error minus f at xn minus 1 by n minus 1th error divided by xn minus 1 into nth error into n minus 1th error. Let us say this is equation number 5 or 4. Now by using Taylor series we can expand f at xn about alpha. So I can write down f at alpha plus xn minus alpha into derivative of f at alpha plus xn minus alpha by 2 second derivative of alpha and so on. Now because this is the root, so this is equal to 0, and hence I can write down, and this can be written as nth error. So I can write down nth error multiplied by derivative of f at alpha plus nth error square by 2 second derivative at alpha, and we'll get higher order terms. And these higher order terms can be neglected because this error is small, so these can be neglected. And similarly I can write down, and this can be written as equation number 5, and for f at xn minus 1 can write down using the same idea this expression. And next I can divide this with nth error, so I get f prime at alpha, that is derivative of f at alpha, plus half of nth error second derivative at alpha, and f at xn minus 1 by n minus 1th error equal to f prime at alpha 1 by 2 n minus 1th error multiplied by the second derivative at alpha. So let us say that this is equation number 7. This is equation number 7. Now using this in equation number 4, I can write down xn minus 1 divided by f at xn minus f at xn minus 1 into f prime at alpha plus 1 by 2 nth error multiplied by the second derivative at alpha minus f prime at alpha minus 1 by 2 n minus 1th error second derivative at alpha divided by xn minus 1 multiplied by product of nth error and n minus 1th error. So here these factors will cancel out and I can write down 1 by 2 f double prime at alpha into nth error minus n minus 1th error divided by xn minus 1 into product of this and this factor, and this factor is xn minus 1 by f at xn minus f at xn minus 1, and we can write down this xn minus 1 as xn minus alpha minus xn minus 1 minus alpha, and so this is nth error and this is n minus 1th error. So this whole thing can be written as 1 by 2 f double prime alpha into xn minus 1 by f at xn minus f at xn minus 1 into nth error minus n minus 1th error divided by nth error minus n minus 1th error into product of nth error and n minus 1th error. And here these factors will cancel out, so n plus 1th error will be given by 1 by 2 f double prime alpha into xn minus 1 by f at xn minus f at xn minus 1 into product of nth and n minus 1th error. And if the xn and xn minus 1 are sufficiently close to the root alpha, then I can write down f at xn minus f at xn minus 1 by xn minus 1 approximately it is equal to derivative of f at alpha, and using this I can write down the previous equation as 1 by 2 f double prime at alpha by f prime at alpha into product of nth and n minus 1th error, and this would be equation number 9. Now this whole thing can also be written as the n plus 1th error, and this factor is a constant, so I can write down it like this, where this constant is this, and this is called asymptotic constant or coefficient. So this is equation number 10. Let us consider that the error is in the form that the n plus 1th error is approximately equal to some constant times the alpha power of nth error. And so I can write down for the nth error will be approximately, or let me take it as m so that there should not be any confusion. So m over here, and from this I can write down it as A inverse nth multiplied by nth error to the power 1 by m. Or I can write down by putting these and these in equation 10. I can write down n plus 1th error is equal to C into nth error multiplied by A inverse nth error to the power 1 by m. So I can write down it as n plus 1th error is equal to C A to the power minus 1 by m and nth error to the power 1 plus 1 by m, and this is equation number 12. Now as we can see from equation 11, we can substitute this value of n plus 1th error in this equation. So I can write down that A to the power A into nth error to the power m is equal to C into A to the power minus 1 by n nth power nth error to the power 1 plus 1 by m, and I can write down it as A to the power 1 plus 1 by m by C is equal to nth power and 1 plus 1 by m minus m. Bringing this here, I can write down. Now this is a constant, so therefore right hand side should also be constant, as n tends to infinity, and this is possible only if 1 plus 1 by m minus m is equal to 0, or m square minus m minus 1 is equal to 0, from which we can find out two roots of this equation. Now negative root is not possible, because then errors will diverge, and so positive root is chosen. And if I solve this, I get m is equal to approximately equal to 1.62. So we see that the convergence is not quadratic, but it is super linear. That is, the convergence is greater than 1 but not equal to 2, and this is known as superlinear convergence. So the convergence is superlinear. Now how this method works, let us understand with an example, and that example is exponential x square minus 1 minus sin x minus 1 is equal to 0. This plot has been plotted here, and we could see that here we have a root and another root lies over here. So to operate this method, what we do, that let us choose f is equal to exponential x square minus 1 minus sin x minus 1. Now let us choose two initial approximations, and these are x not equal to 0 and x1 is equal to 0.5. And using this we can find out that the function value at 0 is equal to exponential 0 square minus 1 minus sin 0 minus 1 is equal to minus 0.632121 at x equal to 0.5. the value comes out to be equal to minus 1.00759. And using this, when we plug these values in the equation as x2 is equal to x2 equal to x1 minus f at x1 minus x0 divided by f at x1 minus f at x0. So x2 can be written as 0.5 0.5 minus f at x1. F at x1 means minus 1.007059. x1 is 0.5 minus 0 divided by f at x1 is minus 1.007059, and minus 0.63 21206. And so if we solve it, we get it equal to minus 0.8429658. This way I have shown it in this table. So as we can see that these are the two initial approximation, these are the values of the function at these x values, and this is what the initial this is what the approximation which we get. Then we choose these two values, and from here we get this one. So let me write down x2 x1. So from x2 x1 we get x2, then from x1 x2 we get x3, and likewise we can obtain other values. Now the stopping criteria for this one is that we can choose that f, the function value at later value of x, is less than the tolerance, or alternatively we can choose that when the two values in the successive approximations become very close to each other. So for example, over here up to 4 digits, here I can see that this is what the root should be. So the root correct to these 4 decimal places is 0.5352. If I choose different initial points, then I see over here that we get different initial approximations. So this is the initial approximation. So using this we get this, and so on and so forth. So as we can see that we can find out other root correct up to 4 decimal places over here, and that is 1.2937. So this is the other root. Now the advantage of this method is that in Newton-Raphson method we need to find out the derivative of the function, and there are situations when derivative of function cannot be obtained. So in such situation we can use secant method. Now there are disadvantages of this method also. Number one is that if the function is not continuous, this method may fail. Number 2, the situation could arise like this, where we have root over here, but we choose 2 points over here, and what we see over here, that these are the initial approximations x0 and x1, and we find out that the next approximation is even farther away from the root, and in such situation we will not be able to find out the root. So a remedy to this could be that we could choose 2 points at the opposite side of the curve. It means that the root remains bracketed between two values, and this method is known as method of false position. It is also known as regula falsi method, Latin what, and also known as linear interpolation, and we shall talk about this in the next video.